Hello everyone, welcome back to my channel. I'm Netra, studying in Sri Venkateswara College of Engineering, Bangalore. So today in this slide, let us discuss about some topic based on maths about bisection method and Lagrange's inverse interpolation. First, introduction to bisection method and Lagrange's inverse interpolation. The bisection method is an iterative numerical method used to find the roots of a function within a given interval. Lagrange's inverse interpolation is a technique used to estimate the value of an independent variable based on a known value function. Introduction to bisection method. The bisection method is a numerical algorithm used to find the root of an equation. It is simple and reliable method that can be used to solve nonlinear equation. The method works by repeatedly bisecting an interval and selecting the subinterval that contains the root. Bisection method. The bisection method works by repeatedly dividing the interval in half and determining in which subinterval the root lies. It requires the function to have opposite signs at the endpoints of the interval. The method converges the root and is guaranteed to find it, but it may be slow compared to other methods. Basic idea of bisection method. The method starts with an interval a comma b where the function changes sign. It successively narrows down the interval until it contains the root. The midpoint of an interval is calculated and used to determine the new subinterval. Bisection method steps. Select an interval a comma b such that f of a and f of b have opposite signs. Calculate the midpoints, that is, c is equal to a plus b divided by 2. Check the sign of f of c and update the interval a comma b accordingly. Bisection method example. Consider finding the root of a function f of x is equal to x power 3 minus 4x square plus 3x plus 1 within the interval 0, 2. The function as f of 0 is equal to 1 and f of 2 as 1, which have the same sign. We need to choose a new interval with opposite sign such as 1, 2. Algorithm steps. Start with an interval a comma b where the function f of x changes sign. Calculate the midpoint. C is equal to a plus b divided by 2. Step 3. Evaluate f of c and check if it is close enough to 0 or it has the same sign as f of a or f of b. Advantages. The bisection method guarantees convergence if the function is continuous and changes sign over the interval. It is repeatedly simple algorithm to implement. The method is robust and can handle a wide range of functions. Advantages of bisection method. Guaranteed convergence if f of a and f of b have opposite signs. Simple to implement and understand. Can be used for any continuous functions. Disadvantages. Slow to convergence. Good intermediate approximations may be discarded. Limitations. The bisections method make convergence slowly for functions with wide intervals or flat regions. It requires the initial interval a comma b to be chosen carefully for convergence. The method does not provide information about multiple roots or complex roots. Requires that the initial interval has opposite signs. Convergence can be slow for function with flat regions, cannot find complex root or multiple roots. Convergence analysis. The bisection method converges linearly with the error approximately having after each iterations. The convergence rate is relatively slow compared to other methods like Newton's method. The number of iterations required depends on the desired precision and the function's behavior. Applications. The bisection method is commonly used in various fields, including engineering, physics, and finance. It can be applied to find roots of equations that cannot be solved analytically. The method is particularly useful when other methods fails or not or are not feasible. Conclusion: the bisection method is a simple, robust algorithm for finding the root of an equation. It guarantees convergence if the function changes sign over the interval. Although it may converge slowly, it can handle a wide range of functions and it is widely used in various fields. Introduction to Lagrange's inverse interpolation. Lagrange's inverse interpolation is a mathematical method used to estimate the value of an independent variable based on a known set of independent variables. It is particularly useful when the dependent variable is difficult or expensive to measure directly. This method involves finding the inverse of Lagrange polynomial, which is a polynomial function that passes through a set of given points. Lagrange's inverse interpolation is a method to estimate the value of an independent variable when the dependent variable is known. It is based on the concept of Lagrange's polynomials, which interpolate a set of data points. The inverse interpolation reverses the process by solving the independent variable given a known function value. Given a set of points x0, y0, x1, y1, so on to xn, yn, and a known function value y. Construct Lagrange's polynomial L0 of x, L1 of x, so on to Ln of x using the data points. Solve the equation L0 of x is equal to y for the independent variable x. Lagrange's inverse interpolation example. Consider the data points 1, 1, 2, 4, 3, 9, and the known function value y is equal to 6. Construct a Lagrange's polynomial L of x using the data points. Solve the equation L of x is equal to 6 to estimate the value of x. Lagrange's basis polynomial. The Lagrange's basis polynomial Li of x is defined as the product of all x minus xj terms divided by the product of all xi minus xj terms where I is not equal to j. It has the property that Li of xi is equal to 1 when I is equal to j and Li of x1 is equal to 0 when I is not equal to j. The Lagrange's basis polynomial are used to determine the weightage of each dependent variable in the Lagrange's polynomial. Inverse interpolation process. The inverse interpolation process involves finding the value of independent variable x given a known value of dependent variable y. First, we calculate the Lagrange polynomial p of x using the set of points. Then we solve the equation p of x is equal to y to find the value of x corresponding to the given y. Advantages: Lagrange's inverse interpolation allows estimation of independent variable based on a known function value. It can be used to interpolate between unknown data points. The method is flexible and can work with any number of data points. Limitations: Lagrange's inverse interpolation may result in inaccurate estimates if the data points are not well behaved. The method can be sensitive to the choice of data points. Interpolation beyond the range of unknown data points may lead to unreliable result. Some of the applications of Lagrange's inverse interpolations are: Lagrange's inverse interpolations find applications in curve fitting and data analysis. It is used to estimate independent variables based on known function values. The method is frequently applied in interpolation techniques for modeling complex systems. Conclusion: Lagrange's inverse interpolation is a powerful method for estimating the value of an independent variable based on a set of known dependent variables. It is simple to implement and provide accurate results when used approximately. However, It is important to consider the limitations and assumptions associated with this method in practice. The bisection method is a reliable technique for finding roots of functions within a given interval. Lagrange's inverse interpolation allows estimation of an independent variable based on known function values. Both methods have advantages and limitations, and their applications vary depending on the problem at hand.